Springs are just everywhere, right? In the pen you're holding, in your car suspension, they're so common that we honestly don't even see them anymore. But what if I told you that this simple, ancient little object is actually at the heart of a massive tech revolution? Yeah. Get ready because we're about to dive into the secret life of the humble spring.
And that really is the question, isn't it? How do you improve something that seems, well, perfect already? It turns out that simple coil of metal we all picture, it's hiding some unbelievable complexity and, honestly, a huge potential for innovation. So this isn't just about making a better spring. We're talking about totally reimagining what a spring can even be.
All right, so here's how we're going to break this down. First, we'll look at how springs are now born from code, as digital blueprints. Then we'll see how they're actually made, the production process. And finally, we'll get into the really cool stuff, the new materials that are changing the game entirely.
So our story starts, maybe surprisingly, not in some noisy factory, but inside a computer. Yeah, before a single piece of metal is ever touched, the perfect spring is designed, it's tested, and it's totally perfected in a virtual world. And this is all thanks to some seriously powerful software.
And the secret sauce here is a technique called finite element methods, or FEM for short. The best way to think about it is like a digital crash test. You take a virtual model of the spring, break it down into millions of tiny little pieces, and then you simulate everything. How will it react to being stretched, or squished, or heated up? You can test it to its breaking point, all without ever wasting a single shred of physical material. It's amazing.
And what's so cool is seeing how different research teams are using this digital power. It's not a one-size-fits-all thing. You've got Zhua's team, for instance, who are basically mixing and matching materials in the computer to dial in the exact stiffness they need. Then you have Sato's group, who are figuring out how to make really complex springs easier to actually manufacture. And Zhua and Zhuang are using these models to make things like robotic manipulators more efficient. See? It's all about fine-tuning that design in the digital world to get the perfect result in the real one.
So what this all comes down to is a concept called multi-objective optimization. And look, it's basically a balancing act. Imagine you need to bake a cake that's not only delicious, but also super healthy, easy to make, and looks beautiful, right? Those things often work against each other. It's the same with springs. You need it to be strong, but also flexible, lightweight, but also durable enough to last for millions of cycles. These are competing demands. But with today's algorithms, engineers can find that perfect sweet spot, that perfect recipe for just about any situation.
Okay, so you've done it. You have the perfect digital blueprint. Now what? How do you take that perfect design and turn it into a flawless physical object? Well, that brings us to the next stage, perfecting the production process. Because let's be real, having a great design on a computer screen is one thing, but actually making it, that's a whole different ballgame.
And this really shows the massive leap we've made. In the old days, just coiling the metal would create all this hidden stress inside, which, could lead to failure down the road. You'd get inconsistencies in the size, and you'd have these huge scrap piles from all the defective parts. But now, we use controlled heat treatments to get rid of that stress. And those same digital simulations from the design phase, they're now used to guide the entire manufacturing process, catching potential problems before they even start.
This whole virtual testing workflow, it's just a total game changer. So you start with your 3D model, your CAD design. Then you throw it into that FIM simulation we talked about, and you push it to its limits. The computer can literally predict, hey, this is where a coil is likely to break. And that lets engineers go back, find those weak spots, and fix them in the design before they've wasted a single penny on materials. It saves so much time and money.
But, even with a perfect digital design, the physical process still matters. A lot. And this is a really important point from Greenville's research. What happens after the spring is shaped is absolutely critical. We're talking about those carefully controlled stress-relieving treatments. This is what lets all that tension, that residual stress that gets locked into the metal during coiling, just relax. It might sound like a small step, but it makes a massive difference for the spring's reliability and safety over its lifetime.
And if you think that's cool, the future of production is even wilder. We're talking about additive manufacturing. You probably know it as 3D printing. This is just blowing the doors wide open. We can now create springs with these incredibly complex, almost organic-looking shapes that were just impossible to make before. It means we can create prototypes super fast and customize designs like never before. All right, this brings us to our final section. And honestly, this is where things start to feel like science fiction. We're moving way beyond just a simple coil of steel. The real revolution now is in the materials themselves, and they are completely rewriting the rulebook.
Seriously, just forget the image of a plain steel spring for a minute. Engineers now have this amazing new toolbox to play with. You've got composites, right? Things like carbon fiber that are super strong and light. You have these wild oxidic materials that actually get thicker when you stretch them. And then you have hybrid designs and even smart materials that can actually react to the world around them.
Just look at this incredible shell core spring. It's a perfect example of a hybrid design. On the outside, you have a metal tube that acts as a strong shell. But on the inside, it's packed with a fiber-reinforced polymer core. So you're getting the best of both worlds, all in a single component.
And this is the whole point, right? By mashing these materials together, engineers can achieve things that were impossible before. They can dial in the exact stiffness they want, they can make it way stronger under compression, and they can make it last a whole lot longer. To truly create something that's way more than just the sum of its parts.
Okay, but what if we could take this even further? I mean, what if a spring wasn't just a passive piece of metal? What if it could have a memory? What if it could remember a specific shape and then, on command, change itself right back to it?
Well, that's the magic of something called shape memory alloys, or SMAs. And this isn't just theory. Check out this real-world example from research by Zhang and his team. They're using it in a thermal management system. So as the system gets hotter and hits a certain temperature, this SMA spring just automatically changes its shape. That movement then opens or closes a valve to regulate the flow. Think about that. There's no external power, no sensors, no computers needed. It's the material itself that's doing all the work. It's incredible.
And look, this isn't just some neat trick for a lab. This is where it gets really important. We're talking about the potential for things like medical implants that can adjust on their own inside your body, or buildings that can physically adapt during an earthquake, or even creating ultra-efficient energy systems. We are literally embedding intelligence into the materials we use to build our world. Okay, so let's just pull this all together. What have we seen? The modern spring is basically the product of three huge revolutions. First, in design. They're born digitally, perfected with algorithms before they're ever real. Second, in manufacturing. Virtual testing makes the production process incredibly precise and efficient. And third, in materials. These new composite and smart materials are giving springs abilities that sound like they're straight out of science fiction.
And that kind of leaves us with one last big question to think about. We've just seen how one of the simplest, most common objects in our world, the spring, is being totally transformed with digital intelligence and smart materials. So, if this is what's happening to the humble spring, what does that mean for the future of, well, everything else?